My name is Savannah Orth, and today I will be presenting my work on the use of enzyme-induced carbonate precipitation to strengthen 3D printed concrete structures. This work was done at Arizona State University in Dr. Nikolath's lab with graduate student mentors Emily Ford and Suraj Nair. This work was overseen by the Center for Biomediated and Bioinspired Geotechnics, and my project was funded by the National Science Foundation's Research for Undergraduates program. Not many people know this, but 3D printing of concrete is a very environmentally and economically sustainable method of construction. You can make some really amazing things like this gorgeous castle that was made by a group in Minnesota. However, there is an inherent problem in this, and that is weakness at the layers, or interfacial weakness. Now, this is a problem because obviously in construction, you do not want there to be a weakness at every layer, up every wall. That is a problem. And so we turned to an existing process to see if we could solve that. That existing process is enzyme-induced carbonate precipitation, or EICP. EICP uses a chemical reaction in enzyme urease to make a calcium carbonate precipitate, calcium carbonate or limestone, to help glue objects together. So we tested that to see whether the EICP treatment could improve the overall strength and the interfacial strength of our structures. This is a structure that we did, and we actually did the EICP process on it. And so all the material on it is precipitate, which is exactly what we wanted, so we could test to see how it behaved when compared to its untreated counterparts. We tested this in a variety of chemical and mechanical ways, and we tested both cement paste and mortar, which involves sand in it. For the chemical testing, we did thermogravimetric analysis, which looks at mass loss and heat to determine chemical composition. In this, we saw that untreated samples had a lot more calcium hydroxide present, indicating that for the treated samples, all of that free calcium was going towards the calcium carbonate reaction. The treated samples also had a second carbonate peak, which was not seen in the untreated. That's indicating that there was the calcium carbonate present. An interesting thing that we found in the chemical testing was that the treated sample, the inside of the treated sample behaved very, very similarly to the outside of an untreated sample chemically, indicating that the EICP process does not permeate the entire sample and does not impact the entire thing, indicating that it's likely most effective as a surface treatment and not for the object as a whole. For mechanical testing, we did compression testing and digital image correlation. Compression testing involves vertical compression using hydraulic presses, and this showed that for both the cement paste and the mortar, the samples treated with EICP were stronger than their untreated counterparts. For the digital image correlation, that was not the case. The mortar samples that were treated actually behaved worse and were not as strong on flexion as the treated samples were, due to the fact that there were aggregates or sand in the mortar that allowed for more crack deflection. And in this picture, it's actually an untreated sample, but we can see exactly this is a crack and it starts to deflect directly along the interface. And that is obviously something that we were trying to avoid. However, it seems that EICP does not actually help with that. It does not strengthen that at the current method. Overall, our chemical analysis showed that there was higher amounts of calcium hydroxide in the untreated samples, indicating the presence of the calcium carbonate, calcium going towards that, and that the current method of EICP does not involve complete permeation from a sample, again indicating that it's likely to be more effective as a surface treatment. The compression testing showed increased strength and less cracking in the treated samples compared to the untreated, so better vertical strength. And then the DIC, or the flexion testing, showed that there was actually less or very little change in the treated versus untreated. In construction, practically this means that EICP is likely more effective on columns versus slabs. Our lab is going to continue to work on this and try and standardize this. As 3D printing of concrete becomes more and more popular, this problem will need to be fixed and need to be addressed. And so further work will be done to be seeing as EICP clearly is a viable method to strengthen 3D printed structures and needs to be further investigated so that it can become industry standard. Thank you.